Now let's look at some examples of functions. And let's start with the doubling function. Again, not as simple as the identity function, but still one of the simplest examples of functions that we use. So I want to name the doubling function f. Remember, f is a very common function name. And I want to be able to double any real number. So that means my input set is going to be all real numbers. And my output set then, if I double a real number, I get a real number in return. So my output set is going to be also all real numbers. So remember, this was one of our types of notation. We named it f, here's our input set, here's our output set. Or here's our domain, and here is our codomain. I also want to give the doubling function in argument notation. So remember, argument notation starts like this with f of x. It means x is going to be our input, or our argument. And there are two different ways I could write the doubling function. On the one hand, to double something, I can multiply it by 2, so 2 times x, or I can add the input to itself, so x plus x. But these are the same thing, so we can use either. We tend to use the 2x just because it's a little bit simpler. So now that we have argument notation for the doubling function, I can write things like this, f of negative 2, and you'll know exactly what I'm talking about. F of negative 2 is going to be, what we're going to do is substitute in negative 2 for x. So we have 2 times negative 2. Well, that gives me negative 4. So that tells me that f of negative 2 is negative 4. We could also write f of 1, positive 1. F of positive 1 will just be 2 times 1. Because I substitute in that 1 for my x. Well, that just gives me 2. So that means f of 1 is positive 2. Now let's also graph the doubling function. So I'm going to set up some axes. So here's x and y. So now I have 2 points that are going to be on my graph. If I input negative 2, I get negative 4. If I input 1, I get 2. So remember, my inputs are my x's, my outputs are my y's. So I get 1, positive 2. That's 1 point that's going to be on my graph. And then negative 2, negative 4 is going to be another point on my graph. Now I could, because I know this is a line, just draw my graph from here. I could just use those 2 points and draw a straight line through them. Just for a little bit of security and peace of mind, let's add one more point. And there's an easy one. If I double 0, I get 0. So I know that my graph is going to also pass through the point 0, 0. So what I end up with is a nice straight line that encompasses all 3 of these points. So there is my graph of the doubling function. Now notice, if this were written in y equals mx plus b or slope-intercept form, I'd have y equals 2x plus 0. That means 0 is my y-intercept, which it is on my graph, so that's good. And it also means that my slope of this line is 2. So what we have here is a line passing through the origin with slope 2, and that's our doubling function, the graph of it. Okay, let's move to a second example. Let's think about g of x is equal to x squared. This one is already in argument notation for us, right? I've given you a name, g, and our input is x, and we're going to square it. If I wanted to write this in words like before, where I wrote doubling function, we would call this the square function. So since I've already given you argument notation, let's take g of negative 2. Again, just means I'm going to substitute negative 2 for my x. So I get negative 2 squared, or negative 2 times negative 2. So notice I kept that negative inside the square, and what I'm going to get is positive 4. Because negative 2 times negative 2 would give me positive 4. I can also take things like g of 1/2. g of 1/2, again, I substitute in the 1/2 for the x, so I get 1/2 squared, or 1/2 times 1/2. So I'm going to get 1 squared on top, 2 squared on the bottom. So that gives me that g of 1/2 is equal to 1/4. Let's graph this one. So again, set up my axes. So this, because it's a quadratic equation or a second degree equation, is going to give me a parabola for my graph. If I tried to factor this one and set it equal to 0 to find the zeros of my parabola, I'd notice that if I factor it, I'm just going to get x times x. When I set that equal to 0, all I get is that x equals 0. So that means the only 0 I know for this parabola is the origin. So I need a couple more points on my parabola to help me out here. I know one. I know that if I plug in -2 or substitute in -2, I'm going to get +4. So there's one point we can put on our parabola. And if I think about it, if I do the same thing with +2, if I substitute in +2, I'm also going to get +4. Then, just to make sure we have the right kind of shape going here, if I plug in or substitute in +1, I'm going to get +1 because 1 squared is 1. Same thing if I substitute in -1. So my graph isn't perfect here, but you get the idea. We get a nice U-shaped parabola for our graph of the square function. Now notice, when I substituted in 1/2, I got 1/4. So if I estimate that 1/2 is going to be about there, and find the point on my graph, that looks like it's about the point 1/2, 1/4. So that confirms for me that that point is on our graph just like we want it to be. Now let's look at a couple other examples. To start, let's look at one that's a little bit different. Okay, so let's look at the equation x equals y squared. So this is in a little bit different format than the rest we've been looking at, right? It's not in argument notation, it's not given in our other notation, it's kind of this other equation. So let's kind of investigate a little bit. We're not used to seeing this. So if I use x equals 1 as my input, I get 1 equals y squared. Now, what we just said was that when I square +1, I get 1. So that means one of the things y could be is +1. But we also just said that -1 squared gives us +1. So y could also be -1. And we don't have a way of knowing which one we want. Either one of those y's will work. Thus, this is not a function, which is why it's not in our normal notation. This equation does not define a function because it's not dependable. If I substitute in 1 for x, if that's my input, I get two different outputs that could possibly happen. So maybe sometimes when I substitute in 1, I'll get +1. Maybe sometimes I'll get -1. So this isn't a function. Another way we could see that is if we graphed it. So if I set up my axes here. So I know that if x is 0, the only thing that I can square to get 0 is 0. So I know the point 0, 0 is on there. And we just said that if x is 1, y is either positive or -1. So what we're going to get actually is a parabola on its side. And just from looking at this graph, it's fairly obvious using the vertical line test that this isn't a function. For instance, if I chose x equals 5 as a value and drew a vertical line there, notice there are two places where that vertical line intersects my graph. if I chose a point over here, so if I chose x equals -2 and draw my vertical line, there's nowhere that that vertical line hits my graph. But as long as at least one time it's going to hit twice, my vertical line test tells me this is not a function. So we know that this example is not a function. So this is kind of a counterexample. But let's go back to talking about functions, because that's what we're really focusing on here. Look at one more numerical example. Okay, let's look at h of x equals 4x squared minus 1. So this is the exact same thing as we've seen before. This is the same argument notation. I'm just naming my function h, just because we've already used f, we've already used g, so I might as well move on to the next letter, right? So, let's think about h of -3. So that means anywhere I have an x in my h of x formula, I want to substitute in a -3. So I'm going to get 4 times -3 squared minus 1. Well, if I square a -3, I get positive 9. So I get 4 times 9 minus 1. Well, 4 times 9 will give me 36, so 36 minus 1 will give me 35. So h of -3 is going to be positive 35. Now let's think about h of positive 3. Well, that'll be 4 times positive 3 squared minus 1. Well, positive 3 squared is also 9. So notice that I'm going to get the exact same thing for h of positive 3 as I did for h of -3. This is also going to be 35. But this is okay. This is still a function because I get one output every time I use -3 as an input. I get one output every time I use positive 3 as an input. So I still have a function here. It's okay if we get the same output as long as for each input I only get one output. So that's just something to note. And these have all been really numerical examples, so let's take some time to think about a non-numerical example, just to solidify our understanding of functions. So what I actually want to do is I want to think about a list of students. So I have my list. I have Beth, I have James, I have Jean, I have Will, and I have Kim. So I have 5 students. So I want to do 2 different things with this list. First of all, what I want to do is I want to give them a table assignment. So maybe we're having a banquet tonight or some other sort of event where they're each being given an assigned table. So we'll say that Beth is at table 1, James is at table 4, Jean is at table 3, Will is at table 5, and we'll say Kim is also at table 5. So notice that no matter where the students go throughout the night, they're only assigned to one table. Beth is at 1, James is at 4, etc., etc. So every time I look at my list or ask someone about one particular student, they're always going to say Beth is assigned to table 1. There's no ambiguity. This is a dependable circumstance where I can ask about Beth as my input. I'm always going to get the same output. So this would be an example of a function. Now let's think about if I wanted to list out the students' majors. And they can have potentially two majors. So let's say Beth is a math major. Let's say James is a chemistry and also education major. Say Jean is a biology major. Will is an English major and an education major. And last but not least, Kim is a history major. So the thing to notice here is that this assignment, for instance, if we want to call it that, is not dependable. If I ask someone about James, someone may say, oh, he's a chemistry major. If I ask someone else, if they happen to be in one of his education classes, they'd say, oh, he's an education major. Or even just looking at this list, James has two possibilities. So does Will. He also has English and education. So this would be an example of something that's not a function because it's not dependable. We don't have that one major for each student correspondence. So this is not a function. So there's kind of a non-numerical way to kind of think about this. Notice that Will and Kim both went to the same table. That was fine. It was fine if two students went to one table, as long as each student was only assigned to one table. Same thing here. James and Will were both education majors. That's okay. The problem is that James is both chemistry and education, and Will is also has two majors. So that's not a function. That's our differentiation here.